In this video, we're going to learn how to estimate derivatives using a forward difference quotient. So first of all, why do we ever need to estimate a derivative? Why can't we just go ahead and use this limit definition? The answer is this limit definition is pretty useful when we have a formula for our function. But we don't always have that formula for the function. Sometimes we're given information about our function in the form of a graph or a table, without an actual formula in terms of x for the function. Okay, so if we're given information about our function in terms of a graph or a table, how do we use that information to estimate the derivative? Well, what we can do is we can estimate this limit by plugging in a value of h that is close as possible to 0. So let's go ahead and write that down. So we have f prime of x is approximately equal to the difference quotient f of x plus h minus f of x all over h, and that is where h is as close to 0 as possible. And this estimation here is called the forward difference quotient when we use h greater than 0. The reason for the name the forward difference quotient is, first of all, this is the difference quotient that we usually take the limit of, and second of all, when h is greater than 0, we have that x plus h is h units forward from x. So this difference quotient then gives us the slope of the secant line between the point at x and the point at x plus h, which is h units forward from x. So let's go ahead and use this forward difference quotient in some estimation problems. Here we are given a graph of f of x below, and we want to approximate the derivative f prime of x at the point x equals 5 using a forward difference approximation. Alright, so why don't we start by writing down the forward difference approximation in terms of some positive number h. Using the forward difference approximation, we have that f prime of 5 is approximately equal to the difference quotient f of 5 plus h minus f of 5, and then divided by h. And again, we're choosing h to be a positive number, greater than 0, and we want to make sure that it's as close to 0 as possible. Alright, so looking at the graph, why don't we first figure out where is the point where x equals 5? Well, x equals 5 is right over here, so here's the point where x equals 5. That point is just 5, 2. Okay, so what is the next point that we're given on the graph? Well, that's just this point over here. And that point is one step forward from the original point at 5, 2. Let's write down from here to here, that's a single step forward, h equals 1. Let's also label that point. That point is at the x-coordinate of 6, and the y-coordinate is across here at 5. So 6, 5 is that point. So plugging in h is 1 into this forward difference quotient, we have that f prime of 5 is approximately equal to f of 5 plus 1 minus f of 5 all over 1. So f prime of 5 is approximately equal to f of 6 minus f of 5 over 1. And let's plug in that information. So f prime of 5 is approximately equal to f of 6 is just 5 here. So 5 minus f of 5. What's f of 5? That's just 2. So 5 minus 2 over 1. So f prime of 5 is approximately 3 over 1, which means f prime of 5 is approximately 3. So So there we go. There is our estimate for f prime of 5 using a forward difference approximation. Next, given the table below, we want to approximate g prime of negative 2 using a forward difference approximation. So let's start out by writing our formula. We have that g prime of negative 2 is approximately equal to g of negative 2 plus h minus g of negative 2 and then all over h. Now again, we're going to be using a forward difference approximation, which means we want h to be greater than 0. We want to be stepping forward to the right to the positive t direction by as small a step as we can. So looking at our table here, let's first look where t is negative 2. Well, that's right over here. And what is the smallest step to the right to the positive direction that we can make? Well, it's just the next column right over here. Now, what is h? H is just the step size. So what do we need to add to negative 2 to get to 0? Well, that's just 2. So let's go ahead and plug this into our approximation. G prime of negative 2 is approximately equal to g of negative 2 plus 2, then minus g of negative 2, and that's all over 2. Let's go ahead and simplify. So g prime of negative 2 approximately equal to g of negative 2 plus 2, which is 0, then minus g of negative 2, that's all over 2. Let's fill in with what we know g is at these points. So g of negative 2 is approximately equal to this fraction. G prime of 0, plug in 0 for t, g prime of 0 is just 1. So 1